Oh shit, that's how it started. Whatever, keep rolling.
Yep.
Ready?
Welcome back to the lab. Today we're going to be studying a tool for math. Now we're going to have some time paradoxes here because we are filming the second video first. So I have to reference a video that doesn't exist yet, and you'll be hearing references to a video that doesn't exist yet.
But when you watch this, it will be in existence.
Right. So the future is the past, past is the future, but it's okay. We're not here to split hairs.
Wibbly wobbly, timey wimey. You know.
Exactly. So what we're going to do is we're going to study the time signatures. We're going to stick straight to time signatures in this particular study. It will relate to harmonics. It'll relate to sections, and it's just a way to consistently analyze different scale levels of frequency. So it goes all the way up. This system goes all the way down to like a tone, like a single tone, and then it goes all the way up to galaxy, universe, as long as relating to frequency and repetition. So we have two categories here. We have a primary category, we have a secondary category. And what we have is two different time signatures. We got 6-4, which is the red, divided into 6, and the 4-4, which is the circle divided into 4. What those are is literally you can use them just as sections. So to one, here, we need a lift pulley. Thanks, pulley. So we have here, no problem, boss. a circle divided into 4. So that means 1R. R is the number of revolutions around the circle. So it's NR, so just 1. So 1 revolution around this circle is 6 beats, or sections. You can't use the word sections, of a certain tempo, which is, we're going to say 120. So this song, the tempo is at 120 musically. There's 6 beats around 1 revolution, so that's 6 beats in 1 measure. And we're going to work with that. So that's the first circle. Can you drop the pulley? Thank you. That works beautifully. And we have a secondary here. Now you notice that there's these two little, fins on the end over here. And that means that once you end over here, it starts back here. Remember, this instrument is playing in 4/4, which means, woo! I love this. 1 revolution around a 4 beat. Oh. You got it?
Yep.
4 beat at tempo.
No problem, boss.
Equals 120 would not make it all the way around the circle in 4 beats. It just wouldn't be possible. So it actually would have to. Now what we have here is, now this is where the math part comes in, because now we can talk about things that really are there. You got 6 sections, you got 4 sections. There's go the same speed around, which means that the one that has 4 beats has 2 less beats than that when tempo is preserved. So that means when the first case goes around once, so 1R around the first circle, and 1R around that. I'm repeating the same thing here. Well, let's say something new. Alright, so now we move on to case 2, which is exactly the same case as the first one, just from a different point of view. So that means we're looking at 6 beats being one full thing. The 4 beats doesn't quite make it around the circle, so what it has to do is go around 1.5 times. Okay, so in order for this circle to get all the way around this circle, or this circle all the way around this circle, it has to go around 1.5 times. So that means in any given piece of music, if you have one instrument playing in 6/4 and one instrument playing in 4/4, it would take 2 revolutions around. I need my notepad. My notebook. Where is my notebook? It's right here. I have all the math written down in here. There we go. So we have 2 revolutions around the primary, P. So 2 revolutions around the primary, so 2 times around that. And we're just going to use that. Doesn't mean divided by in this case, just means and. 3 revolutions around the secondary, means that they'll both be PS will both be on beat 1. Basically means 2 revolutions around primary, 1, 2, and 3 revolutions around the secondary, 1, 2, 3, equals that they both end on the same beat. So in case 2, we have the same exact thing expressed a different way. 1.5 revolutions around case 1, around the 4/4, is equal to 1 revolution around the 6/4, which means 2 revolutions around the 6/4. So in this case, 2RS for the secondary equals 3 times R, which is the primary, which was the secondary up here. So now we have some way to break apart beats into meaningful ways using symmetry. So now we can go on to something like case 3. Case 3. Oh, no, I saw that. Sorry, but the show must go on. So case 3. We have 1 revolution around primary and 1 revolution around secondary are equivalent. But that means that the tempo can't be preserved, because we observed in this case that if tempo is preserved, then it won't make it all the way around the circle. So in this case, 1R of the primary or secondary over 1R of the secondary or primary is both of them on beat 1. So that's the way to use it for time signatures. Now you can use that specific thing to talk about frequency. So now we were talking about these things where, you know, 1 beat is 1 circle. That's the okay. There we go. Scaling. This system works in scaling. So we're gonna say this is 1 beat, right? So we're gonna use that as a starting point and say the entire circle equals 1 beat. Okay. So that means if you divide it into 2, the entire circle now equals 2 beats. So now it takes a longer time around the outside of the circle to finish the whole circle. Now we have here 1R equals 4 beats. So now 4 of these circles make up this 1 circle. They're still circles in themselves because Zeno's paradox and, you know, law of whatever, you could just keep zooming in to do whatever. And now we have here 1 whole revolution is a half a beat, 1 whole revolution is a quarter beat if you go this direction. Now if you notice, when you go right, the numbers multiply, but when you go left, they don't actually multiply. They just become smaller loops of time in a way. So if you start, what you could do is you can take this, start here as 1, then divide that into 2. So that means it's 2 half beats in 1 revolution. So that means this can also be explained as, can you give me some height here? You can have, as the case up there, you have 1 beat is the whole revolution. In this case, 1/2 beat is the whole revolution, which means in this circle, that divided into 2, now that's 1 whole beat around. And it takes longer time. Now what happened, as you can see, this one started here, but this one, you know, it just didn't do that. Just a couple different ways to look at some mathematical relationships. Now I can use this in the study of harmony, in the study of vibration, and any sort of frequency study. It's possible to use it. I'm going to get more in depth with it. I just want to introduce the math system because this is the one I'm really excited about. This is one I haven't really delved into that much yet. So, drop that for me, por favor. Sweet. Here we have a waveform view of any given song. So this is the whole song, 1x. It's the entire song in one whole thing. If you were to zoom in, you know, whatever amount of times, what is that, 1 million times, that you would see this at a certain point, probably at one of these peaks, you would see this happen. So it's the same idea that you can express the divisions of a song, and you can express in the same way the divisions of a frequency. So you can start at 1R equals 432 hertz frequency, actually, and I want to get into that too later on. We use hertz in waves now, but it's actually inverse function of what this is trying to accomplish. So I'm going to start doing all my math in cycles per second, because that'll make it more applicable to this case. So say that 1R equals 432 hertz. Well, then you can split this up into 4, and if you had a waveform that crossed 0 at those points, you would have a harmony if it crossed them exactly, because they both end off at the same point. So you could do that literally all the way up to verses, songs, chords, whatever. You could just keep going with this, and I want to try to analyze some things. It's really relatable to electricity and the study of frequency, but I'm not quite sure exactly how yet. I think that's all I got for the math system right now. Yeah, boring video from you mathematicians out there.
Nope.
Oh shit. Sup?
Camera right, fab.
Oh.
End.